So I wrote a bunch of things on the board that just to remind you where I left off, since it's been like 3 weeks since I talked.
Yeah.
Okay, so our setting, we're working in number fields, which is finite algebraic extensions of the rationals, and looking in the ring of integers that sits there. And the two big results that I want to prove are theorem A and theorem B. So theorem A says if we take jointly intersective families of linearly independent polynomials, then in any measure preserving system, we can make the intersections along those polynomial families basically as good as you would expect in a weakly mixing system along some syntactic set. And the other kinds of families of polynomials, so this was for independent ones, for polynomials that are all multiples of each other. So we're restricted to sort of a one-dimensional space. We also have our results for length 2 and, or maybe this is like 3 and length 4 expressions when we have some, here are some additional assumptions on RNS. So these are just a reminder of the two main theorems that we want to prove. And what I did last time, if I remember correctly, is I showed that these two theorems follow from knowledge of the corresponding characteristic factors. So that was what I spent the last talk on. I showed that, so assuming that the characteristic factor controlling the relevant organic averages in this situation, if you assume that that's the rational Kronecker factor, then you can get this result. And if you know here that it's the Kronecker factor, and here that it's the next complexity nil factor, you can get theorem B. So I just used characteristic factors of the black box to derive these two results, with some details skipped over, but basically shows that. And so what I want to do today is actually show that the relevant characteristic factors behind these results are what I claimed that they are. And I started at least doing the setup of that last time. So there's a general result about polynomial families. There's a general result about polynomial families in rings of integers. If you want to understand some multiple organic average like this, then there's some nil factor controlling the average. And the complexity of this nil factor depends in some maybe complicated way on the family of polynomials, but there's at least some nil factor that controls it. And so what we need to do is reduce from some unknown complexity nil factor to these specific complexities. And so that's the goal for today. And this is going to be about showing some results about equidistribution in nil manifolds. Okay, so I spoke quickly to review that. Do people remember this vaguely? Does this feel good? Okay. So yeah, so what is just a reminder what a nil system is for us. So we have a compact quotient of a nilpotent Lie group, and then we're acting by translations on this nil manifold. So there's some homomorphism for a ring of integers into the group that gives us our various translations. And I haven't actually written down yet what the equidistribution results are going to be. But in any case, if we want to prove some equidistribution results, we can always reduce to, well, not always, we're dealing with polynomial situations here. And in that situation, we can always reduce to the abelianization by a general result of Liebman that I wrote in a little bit more detail last time, but basically says this, that if you want to study the equidistribution of a polynomial sequence in a manifold, then you can, instead of dealing with an actual manifold, you can project down to the abelianization. And I think I said something kind of vague and maybe slightly incorrect about how to think about this. So just a reminder, the way I like to think about this is that it's like a generalized form of Weil's criterion. So Weil's criterion for equidistribution of sequences in tori, or more generally in groups, if you want to know if a sequence is uniformly distributed, you don't have to check for all continuous functions. You can just check for characters, because characters are, or linear combinations of characters are dense and continuous functions. That's what's behind it. And this is saying something similar. We're dealing with a manifold, but once you project down to something abelian, you have characters there. And so you can do this same sort of checking with characters on the abelian level. So I like to think about this as sort of a generalized version of Weil's criterion, and it's very useful. Okay, so we're going to make 2 more reductions, and then I'll state the actual equidistribution results that we want to prove, and hopefully prove them.
So Ethan, I have a question here. So what is the this equidistribution result like? What is its place in your proof? So after you reduce to using Bergelson and Robertson's theorem, you reduce everything to neo manifold or inversely related manifold. Then yes. So yeah, I'm just curious.
Okay, so maybe let me give. I don't know if I fully. I'm going to answer what I think you asked. Maybe I'm misinterpreting. So this allows us. So we want to prove. So what we want to prove is, say, for theorem A, that if we have independent families of polynomials, then the characteristic factor controlling the average is the rational Kronecker factor. So what this theorem says is that we can just assume right off the bat that our system is a nil system.
Right.
And then what we want to show is that if you have a nil system, and the next reduction I'm going to make is actually to totally ergodic, the totally ergodic situation. So if you have a totally ergodic nil system, then you want to show that actually this limit, if the PIs are linearly independent, should be the product of integrals. And so you want to show that some sequence in the nil manifold is equidistributed in maybe x to the k, where k is in our polynomials.
Okay, so you use this equation reverse to show that on rational, right? Because you say that the rationals chronicles is the characteristic for the theorem A, for the
Right.
theorem A. So you want to show that you use the equation to show that on that rational chronicles the average of theorem A is convert to the integral.
So we want to show that if the system's totally ergodic, then you get convergence to product of integrals, because then the rational Kronecker factor is trivial in the totally ergodic situation. And the point is that we can, in the general system, without any other tools, this is maybe incredibly hard, but we can assume that we're starting with a nil system and then showing that something converges to product of integrals is just a result about certain sequences in the nil manifold being uniformly distributed.
I see. Yes.
So yeah, so the second reduction, which actually, so I think in my notes I had this in a better order, but I started giving the abelianization thing last time. The order I'm doing these reductions, there's actually a slight issue with doing them in this order, but maybe I'll mention that after I write it down. So the second reduction, which should really be the first, is that we can assume T is totally ergodic. What I mean by this is if we can show that some characteristic factor is the right characteristic factor for the totally ergodic case, then that's enough for showing it in general for ergodic systems. And the reason for this, let me introduce the definition. So this script P is going to be a collection of families of polynomials. And we say that it's eligible if whenever we have some family in here, three things happen. So the first is that we can remove constant terms and stay in the family. And then we can do what? So if we evaluate along like an infinite arithmetic progression, this should still be one of our families in P, and we can also multiply by constants out front. And this is, say, I guess, for all non-zero C's, such that these multiples are still integer valued.
What is this R in T as?
With what?
PI R in T as?
Oh, that's a plus.
Oh,
This is, I put tails on my T's to try to distinguish,
Yeah.
but that did look very T-like. And yeah, so this is for all RS in my ring of integers, and I guess R should be non-zero. Okay, so this definition is, the term eligible comes from Frantzikinakis, who did something for polynomials in Z, or just upgrading it to rings of integers. And what's helpful here is that, how do I write this? Okay, so let's just say P is some eligible collection. Then if some nil system, some nil factor is characteristic for all families in P, and so for all families in P for totally ergodic systems, then I'm going to say the same is true for ergodic systems. Okay, so basically, I showed last time how to get, so when I was doing the deductions of theorem A and theorem B, I did first, I proved something for totally ergodic systems, and then I like took a power that got rid of the rational Kronecker factor. And that's the same sort of idea that's happening here, and why these assumptions are. So just allowing these multiplication by constants and going to arithmetic progressions gives you a way of getting rid of the rational Kronecker factor. And the first assumption is just to get some convenience so that you can assume that all of your things have zero constant term. Okay, and so I guess I should give examples of eligible families. So the two relevant examples, we can look at the collection of all independent families. Or we could look at, say, a collection of multiples of a fixed polynomial. And I think, let's see, to make this work, I need to assume that the GCD of the L's is equal to 1. Otherwise, property 3 is not going to work. Okay. So this should be relatively easy to check. So if we have independent things, and then we just get rid of the constant terms, they'll still be independent. So here I really mean independent, not linearly independent. So remember the difference is that independent means any non-trivial linear combination is non-constant. No, it's not zero. And then restricting to some arithmetic progression, multiplying by some constant, that's not going to suddenly create dependence between polynomials. And you can similarly check that this satisfies all conditions.
Wait, so are you saying those two examples are examples of eligible families?
Yes. These are eligible.
So this fancy P is a collection of finite sets of polynomials.
Yeah. Yeah, so an element of P is some family like this. And right, so these are both eligible collections. These are the kinds of families you want to study, independent ones or multiples of a fixed polynomial. And so this proposition is allowing us to assume that our nil system is totally erratic. And so I said something about the order being sort of backwards here. I should actually make this reduction first, because once I assume it's totally erratic, that corresponds to the nil manifolds here being connected. And that's actually a necessary assumption for Leibniz's theorem. But this did not depend on this happening first, so it's okay.
And also, if you take the union of those two examples, then it will no longer be an example.
That is
Right.
correct, I think. Yeah, probably. I didn't think about that.
Wait,
No, maybe it is. I think if you take a union of things, it should be fine.
yeah, these properties are preserved under unions.
Yeah. You're right. But I mean, it's not so useful because we want different characteristic factors for these different families, or different kinds of families. Right, so for this kind, we want to show that the characteristic factor is rational Kronecker. And for this kind, we want to show that the characteristic factor is k-1 step nil factor.
Now,
So taking
because the
a union wouldn't be helpful.
right, the proposition does not say there exists a characteristic factor Zm.
Right.
It says if Zm.
So you first have to show that it's characteristic for totally erratic systems. And then what the proposition tells you is because of this eligibility property, you actually prove for all ergodic systems, even if there is some rational Kronecker system.
I see. So even if there is some maximal eligible family, it's probably useless because
Right.
there may not be.
Yeah, that's right. There's probably not a universal M that's going to count, right?
Yeah.
If you take longer and longer expressions, you're going to end up with higher and higher M's, and so it won't be helpful. Okay, so the last reduction is how do I want to call this? Let me just say. Okay, this is not phrased in a way that makes any sense as a reduction yet, but right, so we're dealing with actions of some ring of integers. The group structure here is just ZD for some D, where D is like the degree of the number field. And it's so the easier thing to do is maybe think about ZD actions, and then what do the corresponding polynomials look like? So instead of thinking about these polynomials, what rings of integers were important so that we could actually reduce to a nil factor in the first place. This wouldn't be true if we started with any sort of families of ZD polynomials. But now that we've reduced to nil factors, I want to go back to thinking about things as ZD, because it's just easier to deal with computations. So I'm going to do first a proposition for a single polynomial. So let P be non-constant and integer valued. Then we can write, okay, so let me actually up here, maybe fix an integral basis B1 through B. So an integral basis just means that it's a basis for K as a vector space over Q. And if you restrict to integer combinations of the BIs, you get exactly the rings of integers. So it's a Q basis for the full field, and it's a Z basis for the ring of integers. And we can then use this to sort of expand out polynomials and coordinates. So we can write P of a sum. Like this. And BI should be then a sum so we assume that it's integer valued, which means we can write the result again as a combination of BIs, and this polynomial PI is going to be Z valued. And so this gives us D polynomials from ZD to Z. And what I want to say is that this family P1 through PD is algebraically independent. Okay, so algebraically independent is a much stronger property than linear independence. It means that for any function say for Q with D variables, if f of P1 through PD equals 0, then f is equal to 0. Right, so linearly independent would mean if you took any linear function and this is equal to 0, then your linear function is equal to 0. But this is saying any polynomial combination of the coordinates is going to be non-trivial. And the proof of this is kind of fun, but I want to get to the echo distribution, so skip it. And the second property, which uses this first one also, is that if we take a family that's independent over K, then the family, let me just write it this way. So I is running from 1 to K and J from 1 to D. This is independent now over Q.
Also, I'm sorry, in that previous proposition, are you saying for any non-constant polynomial, those D things that you generate will be algebraically independent?
Yes.
It just suddenly seemed more amazing the longer I looked at it.
Yeah, no, it's a really nice result. So an example, maybe let me at least give an example of what this coordinate thing looks like, because it can be a little bit strange at first. So let's take a simple example. Let's take K to be Q adjoint I, and I'll take the polynomial n squared. So then our ring of integers is the Gaussian integers. So a natural basis to take would be 1 and I. And in that basis, what will we do? We can do P, say, of x plus IY, or just squaring this. So we get what, x squared minus y squared plus 2xy times I. And so the claim here is that x squared minus y squared and 2xy are algebraically independent. And that's true. But this is a very general fact about if you take any polynomial like this in a number field.
It definitely helps to see.
Yeah. So now I've made a bunch of reductions. Let me state a result. So here is the theorem. So instead of dealing with a general mill system, we've abelianized. So we're looking at a torus with just an action, like a skew product action. And then instead of dealing with, say, independent polynomials in a ring of integers, we're going to look at this kind of situation where we have a doubly indexed sequence of polynomials that are independent over the rationals. And so we can phrase a result that no longer actually references number fields in rings of integers, and it's just about z. So I'm going to take d, l, k, and m to be natural numbers. Let me sort of annotate this with what each of these numbers represents. So d and l here are actually both playing the role of the degree of the field extension. There's just for the result I'm going to state, they don't have to be equal, but in the setting of rings of integers, they will both just be the degree. K is the number of polynomials, the number of these polynomials, the doubly indexed sequence, there'll be more. And m is
What is the relation of the doubly indexed sequence?
the dimension, just give me a second, which is going to be at least, I guess, the step within it. Sorry, what was the question?
What's the relation of the doubly indexed sequence to the single index?
Oh, so I'm doing the same kind of expansion. So each of these PIs,
Oh,
you expand in coordinates as PI, sum of PIJs times BJs. Okay, so we have some constants. And now we're going to take a sequence Pij, where I'm indexing I and j is running up to L, and these are polynomials in D variables that should be independent and Z valued. Right, so this is just, we've expanded our family in coordinates essentially. And then T1 through TL will be actions on an M torus that are commuting unipotent affine maps such that they generate an ergodic action. And if you have unipotent affine maps on a torus, because the torus is connected, this action being ergodic actually means it's totally ergodic. Okay, so then we want to prove an equidistribution result. So for almost every x in the M torus, the sequence x is well distributed in the M times K dimensional torus. Let me explain some notation. So Pi is the polynomial Pi1 up to Pil. And this, by this, I mean that, so T is some tuple is the product of the TIs to their corresponding powers. Okay, so I'm just writing it this way for notational convenience, but this corresponds to what the notation means when we were back in rings of integers. we're just, right, so this is T1 to the P11 n times T2 to the P12 and so on, applied to X. And this theorem will imply that for independent families in rings of integers, the characteristic factor is the rational Kronecker factor. Because this is essentially saying that for totally ergodic nil systems, we're going to get convergence to a product of integrals. Because this sort of diagonal sequence ends up being well distributed in the full product space.
Also, unipotent just meant if you subtract the identity from your operator, then it becomes nilpotent.
Yeah, so unipotent, that's right. So
for a matrix, it would just be like. all
it has
diagonal
ones on
times
diagonal, so you should think about these. I'm actually going to write out what the transformation looks like. But unipotent affine map on a torus, you should think about your favorite skew product like x plus alpha, y plus x. That's what we're looking at.
Okay.
But some family of these where they're all commuting. Okay, maybe I'll also say, let me give these numbers so that I can refer to them. So I'll call this theorem 1. And the upper distribution result we're going to need for the other situation is the following. So if U is a sequence with polynomial coordinates, such that its orbit closure is the full torus. And then we take a polynomial with algebraically independent coordinates. Then we can compose with this polynomial, and we will still have the orbit closure being the full torus. This should be Z. So let me give some indication of why this proves the other thing. So when we had polynomials that were all multiples of the same polynomial P, we wanted to show that the characteristic factor is the nil factor of the same step that you would expect for linear averages of that length. And so actually what I want to show is that when you have a totally ergodic system, then the average along for any P is the same as if you replace P by N. So the polynomial averages and the linear averages agree for totally ergodic systems when you're just multiplying a single polynomial. And that's more or less what this statement is saying. So if we have, so our U of N is going to be like you're looking at the sequence on your nil manifold corresponding to some linear situation. So you take, so you're still, your system, your underlying system, you would still have like the unipotent affine transformation. So you have some skew product, which produces maybe polynomial coordinates. And then you're looking in your torus at this particular sequence. And now you replace N by your polynomial, and you want its behavior to be the same. So all I need to do is prove this sort of topological statement, because another aspect of Laban's equity distribution result is that when you have polynomial sequences in nil manifolds, being dense is the same as being well distributed. So we just need to show that their orbit closures agree, and then we will get the result we want.
Oh, okay, so what is the assumption on P? It has algebra.
Algebraically independent coordinates. So that's why I needed this proposition here. If my polynomial was coming from a number field, then it has this property. And so that's why theorem 2 will end up applying in the situation we want.
Okay, I see. Okay.
And this is algebraically independent is the necessary institution for a result like this. And we'll maybe see why that is, depending on how much of the proof I get to. Okay, so I think the more interesting equidistribution result is theorem 1. So let's start with that, and maybe I'll have time to do theorem 2 as well. So as I said, the first thing I'm going to do is just write out what these transformations look like, so we have something that we can actually handle. So first, these transformations Tj commute because we have a ZL action. And this implies that they can be simultaneously triangularized. All right, so if you have commuting matrices, you can simultaneously triangularize them. And so we can assume that these transformations have a particular form, which is exactly, they all have ones on the diagonals and then maybe additional entries, either above or below the diagonal, depending on how we write things. Let me just write it this way. So we're going to have x1 plus alpha 1. This is x by j. Then we have x2, a21, x1, alpha 2, and so on up to xn. And then we sum over the previous coordinates with some coefficients. And we have another alpha. So these are the kinds of skew product systems that we're used to. We just, in each coordinate, we have some linear combination of previous coordinates and some rotational piece. And the sequence that we want to look at is this sequence ux of n, where we apply each of the k polynomials. So this is sitting in the mk dimensional torus. I'll show that this sequence is well distributed. Let's break it into two cases. The first case is going to be the easier case, which is when we're just dealing with some rotations. So the first case is that all of these a's is equal to 0. Which means in every coordinate, we just have a rotation by some alphas. So tjx is x plus some alpha j. And I'm going to let alpha be the map some j alpha j. Okay, so how do we show that something is well distributed in an m times k dimensional torus? Well, one way is that we can take a linear combination of the coordinates to get a sequence in the one-dimensional torus. And if all of such sequences generated that way are well distributed in the one torus, then we have well distribution here. So, I mean, you can, why is this true? Well, any character here is you're just multiplying by like a different constant in each coordinate. And So it's really an application of one-S criterion that I can take this high-dimensional torus, take combination of coordinates, and get a one-dimensional problem. So I'm going to take some collection of coefficients. So I from 1 to k, s from 1 to m. They're non-zero, or at least they're not all zero. And we want to show that this vector of coefficients, if we take their dot product with this sequence, we want this to be well distributed, and we can write this out a little bit more. This is ci dotted with x plus alpha of pin, which is a constant plus a sum of ci dotted with alpha of pin. I want to show that this is well distributed in one dimension. Okay, and how much detail do I want to put here? Okay, let's just say, so for each I do ci dotted with alpha of n. This is the sum of cis and the sum of okay, so what am I doing? So I'm summing over the coordinates. So these are both m-dimensional vectors, and I'm just summing over their coordinates. So I get CIS, and the s coordinate of alpha n is given by this sum here from the definition. Okay, and I can reverse the order of summation. The sum of nj, sum cis, alpha s j. And so if we let, and now this looks like a dot product of n with sums. So that was the point of this switching. So if we let beta be a collection of sums here, so CIS alpha S1 up to Lvid. This should be I. So for each I, we're going to have a vector like this, and then this dot product that we wrote, ci dot alpha, is the same as beta I dotted n. So what does this mean? I've just done a bunch of identities, but the point is we will now get a combination of the polynomials Pij, and then we'll be able to use Wiles equidistribution theorem. So if we're looking at this thing, we want this to be well distributed. What does that look like? So C dotted with Ux of n. If we replace this with this here, we're going to get a sum over I and j of beta ij pij of n. And okay, well now we have a combination of the PIJs. I'm going to skip a few details here. The fact that this system that we started with is ergodic is going to ensure that at least one of these betas is irrational. And so then, because no combination of the PIJs can produce a constant, this polynomial here is going to have an irrational coefficient that is not the constant term. And then, well, okay, if we have a polynomial with an irrational coefficient that's not the constant term, that polynomial is well distributed by Weil's equidistribution theorem. So by Weil's equidistribution theorem, C dot ux of n is well distributed in the one term. And that completes the first one. So as I said, I skipped a few details, but ergodicity is what's going to allow you to get some irrational number appearing. This other questions? You look like you're deep in thought.
I was up a while back, but if you're assuming all the ASRJs are 0.
Yeah.
So you're only assuming that you're rotating the first coordinate by alpha and
And the second part by alpha 2, and so on. So we have rotation still on all the coordinates potentially, but we don't have any.
oh, there's no skew.
There's no skew. It's just a rotation.
Oh, okay.
And what ends up happening is that the independence of the polynomials is the right coefficient to make sure that this is always equidistributed for rotations. So the next thing we're going to do is we're going to now have some skewing happening. And again, we're going to use Weil's equidistribution theorem to get something. So let's see, I maybe want to leave that up. Let me go back here. That's maybe the wrong place to erase. Oh well. Probably should have erased starting there, but too late now. So now we're going to assume that ASRJ is non-zero at least once. So we have some skewing happening. And now, so in the previous situation, we actually showed equidistribution for every x. In this situation, we're going to have to put some assumptions on the coordinates, but it's going to be a not difficult condition to satisfy. So let's take x and the M torus such that its coordinates. I'm also going to throw one in there just to make sure that they're irrational. So I want all of the coordinates to be linearly independent over not just the rationals, but we also want them to be independent from the alphas. So I'll take the rationals and throw in all of the alphas. But whatever. So this is some finite extension of Q. So whatever, I mean, it's not hard to get linear independent things over some countable subfield. Right, I mean, this is, so the situation where you have linear dependence is going to be maybe a union of like lower dimensional subtori. This is definitely a set with full measure. And that's all that we care about. We only need almost every rest of thing. Okay, so now we need to do something with the skewing. And the first thing I'm going to do is let R0 be the maximum of some set. That should be M. Such that ASR is not zero for some S and J. Okay, so I erased how the skew product is defined, but the ASR is the explaining the reliance of the S coordinate on the R coordinate, where R was some earlier coordinate. And so R0 is the last coordinate that appears somewhere later on in the skew product. So the last one is actually involved in any of the skewing. And then I'm going to let capital S be the set of coordinates that refer to the R0 coordinate. These are all the S's such that ASR0 is non-zero for some J. Okay, and so by assumption, this is a non-empty set. And then just some notation. So for any S in capital S, I'll have VS as the set, or sorry, the vector ASR0, 1 up to ASR0, L. And so this is some L-dimensional vector, and it's non-zero because, well, being an S means that one of the ASR zeros is not zero. Okay, so our goal again is we want to show that if we start taking linear combinations of the coordinates in our high dimensional torus, the sequence we get in the one torus is well distributed. And the point of defining these convenient coordinates and vectors is just to pull out a particular coordinate that's going to have really nice behavior. Allow us to use Weil's equidistribution. Okay, so the important claim here is that without loss of generality, by which I mean up to a change of coordinates, we can assume that the set of these vectors is linearly independent. Over the rationals. So this is actually really the key to this result. So let's suppose that we had a combination that is equal to 0. Then I'm going to define a change of coordinates that is going to modify our set S in a way that will get rid of any dependence relation. So I'm going to let S0 be the last coordinate here, where CS was non-zero. And then I'm going to replace the S0 coordinate with this linear combination. So what does this do? Well, we took this combination. So in the new coordinates, the vector VS0 is just 0. right? Because it's going to be the combination of the previous vectors, but that is 0 by assumption. And so we've actually removed, so our set S, our new thing that's playing this role is the same set, but we've removed F is 0. So we've decreased the size of the set and gotten rid of the dependence relation. And so we can just keep repeating this process until there's no dependence relations in the set S. And this change of coordinates is okay because the map that takes X to X tilde it's not 1-to-1, but it's CS0 to 1. And well, this is a finite number, and equidistribution is going to be preserved by finite factors and extensions by some known things about what kinds of objects. So wherever this sequence, whatever its orbit closure looks like, it's going to be some union of subtori, and you can't have a subgroup with finite index. You can't have a closed subgroup of finite index inside a torus because the torus is connected. You have a closed subgroup of finite index. You could then you could write your full group as the union of the finite and many cosets, but now you've written the torus as a finite union of disjoint closed sets, and that's impossible because the torus is connected.
Actually, I think the torus just shouldn't have any finite index subgroups.
Take all linear combinations so take a Hamel basis, remove one basis element, and take all linear combinations of the remaining ones.
Isn't
That's going to be
infinite index because?
Oh, maybe you're right, because that's still like countable index or something. Yeah, maybe you're right. Whatever. It's definitely true for closed groups.
I can prove it after the talk.
Yeah, whatever. What I said is good enough for our purposes because any sequence like this is going to be equidistributed and some close number or union.
That's a fun fact, though.
Yeah.
That's a fun
Okay.
fact as well. I don't mean to diminish this. But like,
So now we want to, so we're just going to assume that this set of vectors is linearly independent, and now we want to finish the proof. So yeah, if you're okay with me going like 5 more minutes.
Yeah, I mean, you started
I started a
5
little
minutes
late,
late,
so.
being patient for us, so
Yeah.
why not?
Okay, so this proves the claim. So now I'm going to take some vector. What are the indices here? I is 1 to k. So again, we're going to start taking linear combinations of coordinates to get something in the one torus. And we're going to make some more reductions. So let's say if CIS is 0 for all I and every S in our set S, then remove the S coordinates and let's just say restart the proof. So by the way that this is defined, I can actually just take away all the coordinates in S, and I still have a well-defined skew product because the S's come after R0, and R0 is the last coordinate that's referenced in the future. So I can just pull out all the S coordinates. Nothing else in the skew product is referencing any of them. And so they can be removed. I still have a well-defined skew product. And now I've reduced to some lower dimensional thing. And so I can, whatever, as I said, you can just restart the proof where you've now removed those coordinates and keep doing this until you have something. It's finite dimensional, it'll eventually get down to some situation where you can't remove anymore. Okay, so we're going to assume that CIS is non-zero for some S and capital S, and get somewhere. object we're interested in is this combination of coordinates of u, which we can write in a particular way. So I'm going to write this as a sum from 1 to n of some polynomials, some combination of the xs's, and then everything else. So this is why I wanted this assumption that they're linearly independent of each other and of all the alphas. Because now I can write everything as a rational combination of the coordinates or some other thing. So if I look at, and erase the skew product, but if you look at any coordinate in the skew product, it's always going to be a combination of the x's, the alphas, and I guess that's it. Right, you're going to get some polynomials with x's and alphas, and we're just pulling off by linear independence. We can separate out all of these polynomials using the independence relation. And so what do we want to show? Well, Weil's equidistribution theorem says if we have an irrational coefficient that's not the constant term, we're well distributed. Here's an irrational number. It's independent of whatever this other stuff is, and of all the other excesses. And so all we have to show is that one of the PS's is a non-constant polynomial. So by, we can state by Weil, suffices to show that one of these is not constant. But we have a special one, R0, that's the one we're going to show is not constant. So why is this non-constant? What does this look like? Let me just write it and then explain why this is the case. CIS. Okay, so we want to look at where the x R0 appears in coordinates of the skew product. So it obviously appears in the R0 coordinate with the relevant coefficient, the Ci of R0. And then it also appears in some later coefficients, all the coordinates in S. And there it appears with this coefficient ASJR0, which is captured by the vector BS. And so we can take BS dotted with the polynomial that's appearing, the ith polynomial with CIS. And those are all the places that the R0 coordinate appears in the skew product, either in its own coordinate or just a coordinate that refers to it. There are no coordinates that refer to it sort of indirectly. This is why I wanted to be the maximum. If I took something that was earlier, like if I took something that R0 refers to, it's referred to by R0, but then there's something else that refers to R0. And as you start applying the transformation, it's going to get pushed into those further coordinates. But there's nothing that refers to any of these coordinates in the future, so we don't have to worry about it. Does that make sense? Okay. And so we just have these two terms. Okay, this is a constant. All we have to show is that this is not a constant. Why is it not a constant? The Pij's are independent. We have something non-zero happening here because the VS's are linearly independent. And so this is non-constant by independence of Pij's and the linear independence of the VS's. So now we have an irrational coefficient with on a non-constant term. And so the sequence is well distributed in the torus, and that's the end of the proof. So, yeah, so I guess I won't take up more of your time. This one's actually much easier to prove. Let me just maybe briefly comment, why is algebraic independence the right thing? Well, we're taking a polynomial of, you can think of this really as a polynomial of the coordinates of P. And algebraic independence is defined as saying polynomial combinations of the coordinates should be non-zero. You just do a little bit to show that, from that to show this. So it's actually not so hard. Once you realize that algebraic independence is the right thing to be working with, and that your polynomials, when you're from a number field, have algebraic independent coordinates. So it takes a little work to maybe get here, but once you have the right assumptions, this result is actually not very hard. So I'll end there.
Thank you.